In case of solid rigid body, we see that the distance between the atoms remains constant, or interatomic distance remains constant, and due to this the material body possesses a fixed shape. But when we apply the external forces to this material body, there is change in the size and shape of the material body, and therefore these forces are called as the deformation forces. For example, let us consider a rubber cord. Now, if we apply the external force at one end towards the right, then we see that the length of this rubber cord increases, or there is change in the length of this rubber cord, and therefore the external force which is responsible for change in length is called as the deforming force, and we say that there is deformation of the material body. It is to be noted that when the deforming force is applied on the material body, there is equal and opposite restoring forces exist in the material, and these restoring forces will try to bring the material body to its initial configuration or equilibrium configuration. Therefore, these deforming forces and restoring forces are always acting opposite to each other. As we go on increasing the magnitude of deforming force, we see that there is also increasing the magnitude of restoring force. So restoring force will try to restore the initial configuration of the material body, and the deforming force will try to change the configuration. Now let us see the definition of elasticity. So elasticity is nothing but the property of the material by virtue of which it restores or regains its original shape or size. As we have seen that we can deform the body, or we change the shape and size of the material body by applying the deforming forces. As soon as we remove the deforming forces, if the body restores its initial shape and size, then we say that the body is perfectly elastic body. On the other hand, if we apply the small forces to the material body, and after removing these deforming forces, the body still remains in its changed configuration, then we say that the body is a plastic body, and the property is called as the plasticity. Now let us see something about the stress. Now, as we have seen that the body can be deformed by applying the external forces. The stress is defined as the internal restoring force per unit area, and these restoring forces are acting in opposite direction to that of the deforming forces. There are three types of stresses depending upon whether there is change in the length, change in the volume, and change in the shape. Now the first one is longitudinal or tensile stress. Suppose the wire is stretched by applying the force F on the cross-sectional area A. Then the longitudinal or tensile stress is given by force upon area, force per unit area. Suppose mg is the weight applied at one end of the wire, and the cross-sectional area of the wire is pi r square. Then the longitudinal stress is nothing but mg upon pi r square. Second type of stress is a volume stress. So here we find that when the deforming forces are applied, there is change in the volume of the material. Therefore, the volume stress is defined as the normal force divided by the area of the cross section. But here this force will result into change in volume of the material body, or it is also equal to the pressure. One more type of stress is the shearing stress. So in this case, when we apply a tangential force, there is change in the shape of the material body. Therefore, this is defined as the tangential force per unit area. The unit for this stress is Newton per meter square, because the force is measured in Newton and the area of cross section is meter square in SI system. Now the dimensions of the stress are m raised to 1, l raised to minus 1 and t raised to minus 2. Now let us consider the term strain. It is usually defined as the change in dimension per unit original dimension. So as we have seen that by using or by applying a deformation forces, either one can change the length of the material body, one can change the volume of the material body, or one can change the shape of the material body. Accordingly, there are three types of strain. The first one, that is longitudinal or tensile strain. So here we find that by applying the force, we can bring about the change in its length. Now as shown in this diagram, we have a rubber cord of length L. So L is the equilibrium length of this rubber tube. Now if we load one end of this rubber tube by applying the mass M, then the weight acting on this end, free end, will be W, that is equal to mg, and one end of this rubber tube is fixed to rigid support. Suppose that due to this weight W, there is change in length, or the new length of this rubber tube will be L plus small l. Then we see that the change in length due to the deforming force, which is nothing but the weight applied at one end, that will be L plus L minus capital L, or the change in length is nothing but small l. So we define the longitudinal or tensile strain as small l upon capital L. This is a dimensionless quantity. The second type of strain is volume strain. So here, by applying the external deforming force, we can bring about the change in its volume. Suppose the initial volume of this rubber tube is suppose V, and when we apply the load at one end, the volume changes to V plus dV. Then we can find out what is the change in volume, that is nothing but dV. So the volume strain is nothing but dV upon V. Again, it is a dimensionless quantity. Now let us consider one more type of strain, that is shearing strain. So here when we apply the deforming forces, the change in shape is observed. For example, as shown in this figure, let us consider the rectangle AHZB. This is a rectangular shaped body. Now, if we pull this body towards the right with the deforming force F, then we see that there is change in shape of this body. We get a parallelogram. So, this type of strain existing is called as shearing strain, and it is defined as lateral displacement of the layer HZ to the distance of that layer from fixed layer. So here we see that HH dash is the lateral displacement of this layer HZ, and divided by distance of this layer from fixed layer AB is nothing but HA. Therefore, the shearing strain is equal to HH dash upon HE, and that is nothing but from figure equal to tan theta, or if theta is small, then shearing strain is nothing but the angle through which the layer gets shifted, that is theta. Now consider Hooke's law. So statement for Hooke's law is, within elastic limit, stress developed within the body is directly proportional to the strain produced in material body. Or we write this as stress is proportional to strain, or stress upon strain is equal to constant. Now, as we have seen that there are three types of changes that are observed in the material body. That is, there is change in length of the material body, there is change in the volume of the material body, and there is change in the shape of the material body. Accordingly, we define three constants, and these three constants are nothing but Young's modulus Y, bulk modulus K, and modulus of rigidity eta. These three constants Y, K, and eta are called as the elastic constants of the material. Let us consider the first one, that is Young's modulus Y, which is defined as the longitudinal stress upon longitudinal strain. So in this case, we find that there is change in the length of the material body when the deforming forces are applied. So the stress is nothing but the force per unit area, and we have found out it in case of the material wire. If it is stretched by applying the weight mg, then the force will be mg and the area of cross section will be pi r square divided by longitudinal strain. So strain is nothing but change in length upon original length. So that is L upon L. So we get the Young's modulus as mgl upon pi r square L. The Young's modulus is only for solids. The second elastic constant is modulus of second elastic constant is bulk modulus K, and it is defined as K is equal to volume stress upon volume strain. So in this case, by applying the deforming force, we can make the change in its volume. So the volume stress, or that is nothing but force per unit area, that is nothing but the pressure dP divided by volume strain is dV by V, or we get minus V dP by dV. Here the deforming forces and restoring forces are opposite to each other, and we write a minus sign here. Now, this bulk modulus is found in case of solid, liquid and gaseous materials. One more constant, that is modulus of rigidity eta, which is also found in case of solids only. So the modulus of rigidity eta is given as shearing stress upon shearing strain. So shearing stress is nothing but the shearing force or deforming force per unit area upon the shearing strain theta, or the modulus of rigidity eta is equal to F upon A theta. So these three constants are called as the elastic constants of the material of a body. And these three constants phi, k, eta are related by this relation. Sigma is equal to y upon 2 eta minus 1, where sigma is called as the Poissons ratio of the material. Now let us consider what we mean by Poissons ratio. The Poissons ratio is denoted by sigma, and it is defined as within elastic limit the ratio of lateral strain to longitudinal strain is constant, and it is found that its value lies between -1 to 0.5. Now let us consider a rubber tube that is suspended to rigid support. One end is fixed and another is loaded with mass mg. Then we see that there is change in length of this rubber tube due to the deforming force mg applied to one end. At the same time, there is change in diameter of the tube. So the Poissons ratio is defined as sigma is equal to ratio of lateral strain to longitudinal strain. So laterally we see that there is change in diameter of the rubber tube, and longitudinally lengthwise we see that there is change in length of the rubber tube. Therefore, we write lateral strain will be equal to delta D upon D. Delta D is the change in diameter upon the original diameter, and longitudinal strain, that is change in length upon original length. So finally we have the Poissons ratio sigma is equal to L upon D delta D upon dl.
If you like this video, don't forget to subscribe, comment and share this video with your friends. Thank you.